Give IUPAC names of the following ethers. Now we are talking about the nomenclature of ethers. Ethers are typically named as alkoxy alkanes. Please note, the parent chain, the longest carbon chain is selected as alkane. And ethers are not appearing in suffix. They are placed as a prefix. That means that they are not given very high priority. As a matter of fact, everything which appears in prefix has same order of priority, and which is the minimum priority, the stupidest of groups actually. So just take a look at this. You have CH3, O, CH2, CH, CH3. Sounds good. So if I choose the carbon chain, now ether is attached to this carbon, right? So let's take this as the longest possible carbon chain. Yes, this looks like a very clean longest possible carbon chain. In this case, this is the ether. So this is the longest possible carbon chain. Yes, this is the longest possible carbon chain. Now having selected the chain, what goes next? Name it, count it. 1, 2, 3. 1, or maybe 1, 2 will count later. Well, 1, 2, 3. This means this is a methyl group. This is ethoxy. Ethoxy starts from E, methyl from M. E comes before. So 1 ethoxy, 2 methyl propane. Is this the name? Yes, this is the name. What about this one? Now, carbon chain is just 2 carbons, ethane. I have Cl as chloro and this as methoxy. Chloro starts from C, methoxy starts from M. First alphabetically is chloro, and please note priority order of all prefixes is same, it is only alphabetical. So 1 and 2, this is the way we should number it. So this is 1 chloro, 2 methoxy ethane. Wow. 1 chloro, 2 methoxy ethane? Yes, indeed. What about these two? Well, you have C6H4. Now, this looks like a benzene ring, a para position. So, if I have something attached to a benzene ring, then the parent chain is, well, very well the benzene ring. Right. Methoxy and nitro, LMNOPM comes before. So, this is 1, 2, 3, 4. 1 methoxy, 4 nitrobenzene. And are you aware that methoxybenzene is also called anisole? So one popular name could have been para nitro anisole also. But then this is not a systematic name. IUPAC name is this only. What about this one? Well, again, let's see the longest possible carbon chain. And that would be this. Yes. 1, 2, and 3 carbons. Oh my God, this is as simple as it gets. 3 carbons is propane. So this is 1, 2, 3. Methoxy. This is methoxy. Propane. 1 methoxy, propane. Give IUPAC names of the following ethers. Wow. Let's see. 5th and 6th. What do they say? Well, this is the parent chain. Very well. This is the parent chain. This one. Benzene is a chain. Yes, benzene is the parent chain. Having fixed the parent chains, 2 substituents are better than 1. So first, this is number 1, 2, 3, 4. This is the way we choose. Why? All substituents have same order? Yes, they have. If I take this as first carbon, when is the next branching? On the same carbon. So this has higher priority. Now we don't look at alphabetical order. So this is now 1,1 dimethyl. I'm sorry, this should come later. Ethoxy comes with the 4 ethoxy, 1,1 dimethyl methyl cyclohexane. Wow, this is the name? Yes. You might be confused that number is 1, but I'm writing it afterhand. So there are two different issues. One is, how do we decide locants 1, 2, 3, 4? How do we assign the numbers? That is a different rule. And while writing, we don't look at these numbers. We don't look at prefixes like di, tri. It is just alphabetical. Ethoxy is from E, and dimethyl has methyl M, which is from M. Numerical prefixes like di, tri, they are not considered while deciding the alphabetical order. E comes before M, so I have to write this before. These numbers are not important while deciding the alphabetical order. But why should I name this as 1 and not this as 1? Because this is ethoxy. The rule is very simple. First of all, number 1 should go to the highest priority functional group. There is no highest priority functional group which appears as suffix in this case. All are prefixes. Methyl is a prefix, ethoxy is a prefix. Then let me look at carbon, which has maximum number of branches. And had there been same number of branches, then I would have come to alphabetical order. But already more branches here, so I name this as 1. This is what I get. This is the name. This is very simple. Ethoxy benzene. Parent chain is benzene, so this is simply ethoxybenzene. Preparing ethers by Williamson synthesis, and we have 1-propoxypropane. Now what is propoxypropane? 1, 2, 3 carbon, so this is propoxy, and this is main chain, so this is 1, 2, 3. So 1-propoxypropane has to be prepared. How do I do that? Well, it looks like that this is the bond I'm supposed to make. How would I do that? 1, 2, 3. I will take this sodium propoxide and I will make it react with 1-chloropropane. Williamson synthesis. Dry ether is the solvent. I'll get this. That's it. Ethoxybenzene. Now, ethoxybenzene looks like this. Please note, Williamson synthesis is not possible with halogen attached to benzene ring. So what we should do is, we should have oxygen already attached here. Sodium phenoxide, right? And when this attached, this reacts with ethyl chloride, then I think we will have what we desire, that is, see, SN2 attack like this, and that would be the product. This is what we need. Sodium phenoxide and chlorobenzene. How do I get sodium phenoxide? If you are still confused about that, that's very simple, my dear. You take phenol, you add NaOH, you get a salt, sodium phenoxide, that's it. So phenol and ethyl chloride are the substrates you need, the reagents you need, with NaOH. You react them and you get this. 2-methoxy, 2-methyl propane. Now 2-methoxy, 2-methyl propane. Well, if you see, there are two ways in which you could imagine. See, oxygen-carbon bond you have to make. Now, one imagination could have been, I'm just drawing the imagination bubble, and the other imagination could have been these. And you have to tell me which one looks good to you. Well, it could have been that this is a new bond. So I have CH3, O minus, and I have tertiary butyl chloride. This is one imagination. I have this and this is separate. This is a new bond which I'm going to establish. Does it look good? No. Why? Unfortunately, this is tertiary alkyl halide, and in case of tertiary, this reaction fails to occur. It is a bad idea. It's a bad idea. No. Other possibilities, say this is a newly formed bond. So I have CH3, Cl, and I have tertiary butoxide ion, and yes, This can react to give me my product? Very much. This is correct. So sodium tertiary butoxide with methyl chloride would give you 2-methyl 2-methoxypropane. 1-methoxyethane. This is ethane, right? This is 1-methoxy. I think it's as simple as it gets. You have CH3ONA reacting with CH3, CH2, Cl. Can I get that? Yeah. In this case, you are making a new bond, and that bond is this one. This is the new bond you're making. Because as there is an attack here, huge, you find that is a new bond which is done. Could I have made this as a new bond? You also have one more possibility in case you wish. Sorry. Or you have CH3Cl plus CH3, CH2, ONA. Is this also a possibility? This is also a possibility. You'll get still this. Which is a good one? Both are good. You can take any one. This I feel is slightly better. But both are very, very happy ways. You could do it any way you like. Illustrate with examples the limitation of Williamson's synthesis for the preparation of ethers. Well, when you actually carry out Williamson's synthesis, please understand that the mechanism is SN2 mechanism. So all the reactions for which SN2 mechanism does not work very nicely would be the cases in this question. What do I mean? I'll just exemplify with some cases, like say for example. Now first let me write down what is Williamson's synthesis, and then we can talk about the limitations. If I have a case in which RO minus alkoxide ions react with alkyl halide, well, there's a lovely backside attack, classical SN2 reaction, and I get RO R dash plus Cl minus. This is the method, the Williamson's synthesis method to obtain ethers. Okay, fine. Now, which are the cases which won't work? Do I have any constraint on RO minus? Actually none. It could be just anything. Alkyl group could be primary, secondary or tertiary. It could be present even at a bridgehead position. It could be aryl group, benzene ring, whatever. There is no constraint. It can be absolutely anything, as long as it is an alkyl group. This presents a problem. What? Why? See, R dash has to be primary. Best is if it is primary. Even if it is secondary, it's okay. But R dash can never be tertiary. R dash can never be vinylic. It can never be phenylic. Why? Why these constraints? Let me give you 3 examples. They're asking about limitations of Williamson synthesis. So the limitations are the limitations as prescribed by SN2 mechanism. The first limitation is R dash Cl cannot be, in R dash Cl, R dash cannot be. R dash cannot be tertiary. Why? In case of tertiary, a substitution doesn't happen. Unfortunately, an elimination would occur. E2 elimination dominates in the case of tertiary. There is a reason why we can't use tertiary. What do you mean? We don't understand. I'll give you an example. Take a look. Say we have CH3, O minus. I'm just keeping it simple. And say we have CH3, C, Cl, CH3, CH3. So first of all, in tertiary, there's too much of steric crowding. For an SN2 attack, this attack has to happen at this location. I'll just show you. it has to come here. This is very light. Yes, it is light by design because this doesn't happen. It is a difficult reaction. On the other hand, much simpler is if it takes away this H plus. Oh my God, what happens? This happens. CH3OH, it has taken away H plus. This CH2 group now forms an alkene. It has pushed away, Cl minus has pushed. It has no respect. It is always kicked out. But in which style? This is not SN2, it is E2. And unfortunately, you don't get an ether, you get an alkene as the major product. So, R dash cannot be tertiary. Why? Because if you use tertiary alkyl halide, you would get alkene as the major product and never an ether. Reason being, steric crowding around tertiary carbon atom does not allow an easy approach of nucleophile on tertiary carbon. This is the first limitation. Is there a second limitation? Yes. Vinyl halides do not give Williamson's synthesis. I have a limitation of space, I am not writing down the grammar sentences, but vinyl halides do not give Williamson's synthesis. What does that mean? It means that if I have CH3O minus and if I have CH2 double bond CHCl like this, and if I try to react them, actually nothing happens. There is no reaction. They just don't react. Why? Why? Because this bond is very, very strong. Stronger bond by sp2 carbon. This carbon atom is sp2 hybridized. This bond is stronger. Not only this, these lone pairs are in conjugation with this pi bond, making this sigma bond even stronger by some pi contribution. So since leaving group is no longer a good leaving group, why? Because the bond formation is stronger. Nothing happens. It just doesn't leave. It refuses. In the same fashion, the third point, aryl halides do not undergo Williamson's synthesis. CH3, O minus once again, plus say you have chlorobenzene. Again, this bond is stronger. It doesn't break. And there has to be a backside attack in a SN2 mechanism. And for backside attack, you can't break through benzene ring and you can't destroy the ring and just attack from the backside. It is just not possible. What happens? Nothing happens. There is no reaction. Vinyl and aryl halides fail to react, while tertiary halides produce an alkene. These are the three classic cases where Williamson synthesis cannot be done. How is 1-propoxypropane synthesized from propane 1-ol? Write the mechanism for this reaction. Okay. Now I have propane 1-ol. And I am expected to synthesize 1-propoxypropane from it. Well, like this. How do I do that? Doesn't sound very difficult. Just add sodium. You get alcohol becomes alkoxide. Hydrogen escapes. It goes away on its own. You have to do nothing about it. And then, what do? Well, you add alkyl halide. And this can just attack and push it out. That's it. So you have 1-chloropropane. That's it. In case you're even more miserly and you have intentions not even to use this as an initial starting agent, you say that I just have propane 1-ol, then I even have a parallel method for you. Half of propanol, you add sodium, you make propoxide. The other half, you start from this. This is your starting point, right? And then you add SOCl2, Darzin's reaction. No rearrangement, nothing. OH group gets replaced by Cl group. That is the beauty of Darzin's reaction. You add SOCl2, alcohol changes to alkyl chloride. So half of it is alkyl chloride, half of it is alcohol. Then you react them together. And this is the product. Right? That is a very brilliant synthesis of 1-propoxypropane from propane-phenol. Also, people have mentioned, right, mechanism for this reaction. Well, let me relate that. I have 1 propoxide, lovely, and I have Cl, H, CH2, CH3. What is this? 1-chloropropane. And when they react, my dear, there is a backside attack. Fanciful. There is formation of an unstable intermediate, Cl. This entire group is ethyl. I'm just writing Et instead of this. And on this side, I have O, ting, tang, ting, propoxide ion attached like this. It is approaching and it is pushing Cl out. Finally, there is success. Chloride ion is pushed out indeed, and I get C, H, ethyl, O, ting, tang, ting. Wow, this is the product? Yes, this is the product, this is the intermediate, and the mechanism is called SN2 mechanism. This is the very classical SN2 mechanism. Preparation of ethers by acid dehydration of secondary or tertiary alcohols is not a suitable method, give reasons. Well, actually what happens is, when you're carrying out dehydration of alcohols, you use concentrated sulfuric acid. So, for an example, let us take tertiary butyl alcohol. What do? The moment we use H plus from H2SO4, please note, a lone pair is donated by OH group to H plus, and I get OH2 plus like this. The OH group, which was a poor leaving group, let me remind you, the OH group, which was a poor leaving group, now becomes a good leaving. This was a poor leaving group, very horror-like writing, and this now becomes a good leaving group. Okay, so what happens? So what happens is, I love this, huh? It just leaves. If they're a good leaving group, what will happen? They will just leave. Oh, I don't like this much. I'll rather stick to this leaves. This group leaves. And as they leave, they generate a lovely carbocation like this. And well, what happens is this. Carbocations, have a great tendency. What? They have a tendency to lose H plus. And very naturally, just like, if there are dry leaves on a plant or on a tree, there's a small breeze also, they just they just fall away. In the same fashion, you find that this H plus is dying just to leave. Carbocations have a great tendency to push away H plus and form alkenes. Oh my God. So what happens? So you start, actually my dear, you start getting alkene. This is called even elimination. You start getting alkene. But we wanted ether. That is the problem. Secondary and tertiary carbocations are reasonably stable, and especially tertiary. So invariably you will be pushed in direction of getting an alkene. It's not that you will get 100% alkene, but you get enough of it to get sick of it. It's a useless byproduct. It is spoiling your reaction and efficiency. Then why take this route? Choose some other route. Choose Williamson synthesis, for example. Right? So That is why preparation of ethers by acid dehydration of secondary or tertiary alcohols is unsuitable, because they begin to give alkene as a significant and undesirable byproduct in larger quantities by even mechanism. Write the reaction of HI with 1-propoxypropane. Wow. Now, this propoxypropane has become quite a rage. And if it reacts with HI, what happens? Well, HI cleaves ethers. Okay. So what happens? What happens is you get OH and I. HI, this bond breaks. You can say why this and why not this? Both are symmetric, you can break any of these bonds. This is what you get. This is the equation. What about methoxybenzene? Well, OCH3. Now please note, oxygen with anything with aromatic ring is very stable. So it is not easy to break this. This bond does not break. This is strong bond. Please remember, all the bonds with aromatic rings are strong. They are not very likely to break very easily. So instead, there is a choice. This bond breaks, and hydrogen goes always with oxygen. So naturally, iodine goes to the other one, and yes, this is the correct answer, and that would be the product of cleavage of ether by HI. Benzyl ethyl ether. Even more interesting. This is benzyl ethyl ether. Attach H plus. Let us see what happens. This is what is obtained. And do you know that benzyl cation is very stable? So it just gives you benzyl cation and CH3, CH2, OH. We have ethanol. Yes, you have ethanol. And you have benzyl cation. I minus can simply attach itself to give you benzyl iodide. Wow. So this is SN1 mechanism. The classic mechanism is SN1, and the products are benzyl iodide and ethanol, like this. Explain the fact that in alkyl aryl ethers, the alkoxy group activates the benzene ring towards electrophilic aromatic substitution, yes, and it directs the incoming substituents to ortho and para positions in benzene ring. Let's consider an aryl ethyl ether. Well, OR, this is aryl alkyl ether, not ethyl, alkyl, any alkyl for that matter. And now say any electrophile E plus happens to approach this. There are many places where E plus can approach. Let us say, and let's not forget that one hydrogen is already there, right? E plus can approach it in many ways. Ortho positions, meta and para. Just to make sure why it comes only at ortho and para and not at meta, I'll give you all three examples. Say it goes to ortho position. Can I draw the intermediate in that case? H and E. I have a plus here, like this. This is what is formed at ortho. At meta and at para. Let's see what happens at para. We have this, and if we have electrophile approaching here, this would, across a double bond, on one side you attach, on the other side you get plus charge. That is the way to do this. Is there possibility of resonance? Yes. plus M. What about this? Look at this. This comes here and this comes here. Okay. So what do you get? Allow me to draw contributing structures for you. OR plus this and this, H and E. What is this? OR plus H and E, like this. What about the meta one? Well, the meta one goes like this. OR H and E, then I will get a plus charge here. Now please see, in these contributing structures, octet is complete. Oxygen is directly in conjugation. It is donating very nicely. What happens in this case? In this case, if you care to note, this plus charge, if there is resonance, it will transgress this. It won't allow the lone pairs on oxygen to participate in conjugation. It is this. It can come here, it will come down. But this lone pair is unutilized. There is no direct conjugation of oxygen atom lone pairs. That means the plus M of OR is not used here. OR was a very powerful electron donating group. Only minus I is operating here and not plus M. So this is useless. So meta substitution is a bad one. Why? Because my rhenium ion is not stabilized equally. In fact, it is being destabilized by minus I effect of RO group. Plus M is not valid here, and in this case there may be minus I which is insignificant. Plus M is so powerful that it has stabilized the intermediates. That is an absolutely real beauty. We should have it, and we will have it, and we do have it, and we have it. So there we are, and that is why we say that it directs the incoming substituents to only ortho and para and not to meta position. Why? Because OR group is an electron donating group which uses the lone pair on oxygen atoms for delocalization in the adjacent carbocation or benzene ring for that matter. Right? There we are. Write the mechanism of the reaction of HI with methoxymethane. Methoxymethane is the simplest ether, and as you intend that it reacts with HI, what happens? Well, there is a donation. A lone pair is donated, and H plus gets attached here, just like this. OH CH3 CH3 plus I minus, right? And it goes here, it gets pushed here. What do I get? I get CH3OH plus CH3I. Oh wow. Methanol plus CH3I? Indeed. What is this? This is classical SN2 attack. It's a backside attack. I have C, H, H, H. This is methyl. On one side, you have OH plus CH3, this group. And on the other side, you have incoming I minus. And as I minus comes in, it pushes out methanol. So you get methanol and methyl iodide as two distinct products. This, of course, is the intermediate or the transition state, trigonal bipyramidal transition state. This is the mechanism for the reaction. Write the equations for the following reactions. Friedel-Crafts reaction, alkylation of anisole. What is anisole? The first barrier is people forget what is anisole. Anisole is methoxybenzene. Okay, and can we carry out its alkylation? Yeah, very well. How exactly? Well, we use AlCl3 and anything else? We use methyl chloride. What do we get? Or RCl. I mean, it is alkylation, not methylation. I could have used any alkyl group as a general item. I think it's better to write down RCl. What happens? I get two products. First of all, please understand that anisole itself is highly activated because of the very strong and powerful electron donating group OR. What would I get? I would get substituents at ortho and para positions R and R. This is Friedel-Crafts alkylation of anisole. Nitration of anisole. Can we nitrate it? Of course. Anisole itself is highly activated towards electrophilic aromatic substitution. So we just use dilute nitric acid for its nitration. And what do we get? We get, again, it is ortho para directing group. So we get ortho, but this is para, this is major. Why? Bulky OCS3 group, it keeps on moving around and it does not allow any other group to sit easily on the neighboring position of ortho. So you do get ortho, but it is minor. This is ortho. Para is major, and this is what you get on nitration of anisole. Bromination of anisole in ethanoic acid medium. Well, OCH3. This is anisole. We add bromine. Please understand, anisole itself is activated, so no separate catalyst is required. We have acetic acid medium. Fine, good enough. What do we get? We could get again ortho, or we could get para substituted product. So what? What do we actually get? Largely we get para. Why? Bulky group of OCH3 and Br itself is bulky, they stay away from each other. You do get some ortho, but this is little, it is minor product and major is para product. Friedel-Crafts acetylation of anisole. This is most interesting. Why? You have OCH3, great. Acetylation means you have CH3, COCl, acetyl chloride and AlCl3. Lovely. Acetyl group is huge and OCH3 also is reasonably large. So largely you would obtain a para product. Although you might assume that there might be some minor ortho product, very little. Largely it is going to be a para product only. Show how would you synthesize the following alcohols from appropriate alkenes. Now, if this is the alcohol, please understand what is the method of actually getting back to alkene. Whichever carbon it is with, mark it as alpha carbon. And the neighboring carbons are, my dears, beta carbons. Alpha, ting, tang, ting. The neighbors are beta carbons. And all you need to do is to remove one hydrogen atom from beta, H from beta and OH from alpha carbon, and see what appear to be the possibilities. If I take beta 1, if I remove OH, I would get CH2 like this. If this and this are symmetric, so there is no significant difference. I'll get this. So these appear to be two possible alkenes. These appear to be two possible alkenes from which I would be able to obtain this alcohol. Yes, In which way? By simple hydration of alcohol. H plus, H2O, H plus, H2O. Which is the correct answer? Both are the correct answers, and they are mentioned. How would you synthesize the following alcohols from appropriate alkenes? There are two possible appropriate alkenes, and from in any of them, if you add acid and water, you would get the alcohol which is desired. The same trick again. This is alpha, this is beta, and ting tang ting, ting tang ting. Since they are same, I have just given the same name, beta 1, this is beta 2. Once I'll remove from beta 1, I get this. Once I remove from beta 2, I get this. These are the two possible alcohols. Very interesting. And to either of them, again, if I add H plus and water, I get this. In both the cases, Markovnikov addition will give me this hydrated alcohol only. The third alcohol is a bit more tricky. Alpha, beta 1, beta 2. Now just imagine. If I make a pi bond like this, HOH, Markovnikov addition, I get this. This is fine. If I take beta 2, there is a problem. If I hydrate this, H and OH, OH can come on third location, H and OH, OH can come on second also. So half of it would be this and half of it would contain OH at third location. Now that is really bad. So this is not the correct route. No, this is not the correct route. Let's reject this. Only one possibility. This is the appropriate alkene. But you told a method of taking beta 1, beta 2. These are the possible alkenes. You could have got this from all these possibilities, but you must cross check and see, are you getting back the same as the major product or something else as well? Please cross check. That's very necessary. How about this? Very interesting again. Alpha, beta 1, beta 2 and beta 3. Let us see. I'm just exploring all the possibilities. With beta 1, this would have been the alkene. If I hydrated Markovnikov product H and OH, H and OH, yeah, do I get that? I seem to get that. That sounds pretty much okay. Fine. H plus H2O. What about beta 2? Secondary and tertiary. H and OH will get attached here. Will I get this? Yes, I will get it. Same. No problem. These seem to be the possibilities. Beta 3, H and OH. Now both are tertiary. Both these locations are tertiary. I could get H, OH. I could also get reverse H and OH. So half of it will be this. Half of it would contain H here and OH here, which is bad. I don't want that. So this is not a good option. There are two possible alkenes which on hydration with H plus and water, any acid added to water, dilute acid, would give me this alcohol. When 3-methyl-butane-to-all is treated with HBr, the following reaction takes place. Oh my God. OH goes away from here. Strangely enough, this hydrogen also runs away, and you find that the CH upgrades itself to CH2, and suddenly I have Br getting attached here. Give a mechanism for this reaction. Okay, sounds very interesting. Let's see what happens. First of all, 4 carbons. This is the molecule. I'm just drawing the same molecule here. The moment I add HBr, is there a mechanism involved? Yes, a wonderful mechanism. And how's that? Watch it with me. One of the beautiful reactions of organic chemistry, you will have OH, H. Br minus is just separate. First step is protonation, attachment of H plus. I get, this is a poor leaving group and this gets converted to a good leaving group. And the moment you have a good leaving group, what does a leaving group do? It leaves. So it just leaves. How stupid. Call it stupid or whatever you want, but yes, it does leave. And this is the first step of the so-called SN1 mechanism, generation of carbocation. A carbocation is born. Then suddenly we notice this is just a plain secondary carbocation. Yes, and there is a possibility that this carbocation can change itself. What? How can it change itself? Well, a neighboring hydride along with electrons can jump. Can it? Yes. And this is what is popularly called as hydride shift. And the moment it jumps, please note this hydrogen is coming with two electrons. So -1 charge, one electron was the personal electron of hydrogen. The second one it takes from the carbon, and along with both the carbons and the electrons it jumps. If it jumps, well, this is what you seem to get. There is a new hydrogen here, and there is a plus charge here. So the nature of carbocation changes. There is a hydride shift, and this is the carbocation. And finally, and this happens very rapidly, less than a nanosecond before anybody can imagine, hydride has jumped. Bromide ion is ready to attack. It comes and it attaches itself simply to the place where there is a plus charge. I get this as the product. Classical SN1 mechanism. And is this the product? CS3, C, CS3? Yes, CS3, C, CS3. And Br is attached to the same, and then you have CH2, CS3. Precisely. This is what you obtain as the final answer. This is the product. And that, my dear, is the detailed mechanism of how this reaction happens. So, my dears, you find that this was the chapter of alcohols, phenols, and ethers. The questions of NCERT are pretty much simple here, but nonetheless, they are very fundamental and useful. I'm sure you're going to benefit from them. And if you want more, don't forget to download our app, Vyas Certification app. This is Shishir Mittal from Vyas Certification, Kota. Wish you all the best for your preparation. Have a great time.